So, what we will do next is we will go to a 2D case, okay, and we will spend a lot of time on 2D because the scattering problem which we had started with was a 2D problem. So, we will be using this Green's function, okay, right. So, let us go to the 2D Green's function, right. Now, let us look at the wave equation that you are all already familiar with because you have seen it once or twice before. This is the wave equation that we had written, right. How did we arrive at this? We had taken Maxwell's equations, right, and made some simplifying assumptions. What were they? For example, I had considered TM polarization, 2D problem, all of those assumptions I had made, and I had written it in terms of the variable phi. Phi was my Ez from the previous module. So, this equation we are familiar with. We were also familiar with the definition of the Green's function. We had used this kind of a relation. Okay, so again, so this is mostly revision for you all. If I wanted to use the theory of Green's function, I would calculate this g once and then use it for whatever f is given to me. That is the idea of Green's function. So, the first step is to calculate or rather solve this equation over here. Again, repeating from our previous few slides, what would be the recipe of these equations, say 1 and 2? What do I start with? Remember, objective is phi in terms of g and f. That is what I want. For that I need g, right. So, of equation 1 and 2, what do I begin with? 2 multiplied by what? F of r prime, right. So, I take this guy multiplied by f of r prime and then integrate both sides, right, with respect to primed coordinates, right. So, because I am multiplying by prime coordinates, I can, this is just once again I will write it. So, f of r prime goes in because the operator only acts on the unprimed coordinates. Right. And then the next step was integrate. And when I integrated, it looked just like equation 1, right, and from that I concluded that my phi of r was equal to the integral over v prime f of r prime g r prime d, let us call it dv prime, okay, or dr prime, whatever, okay. That minus sign has come because here the definition has a minus sign over here. Right, when I integrate on both sides, I'll find this minus sign. Just convention.
Initially you took plus 1.
Initially did we no, because here yeah, it's just a matter of convention, okay. There's no great mystery to it. Once you fix your definition from equation 2, all the minus signs take care of themselves, okay. So, primarily in this example I am keeping the minus sign because the reference material which is there for reading, they also assume a minus sign which is in Chu's book. So, when you go back to reading those notes, you shouldn't get off by a minus sign each place, okay. But just know that it's just a matter of convention.
So, it means just g gets flipped.
Yeah, that's all, absolutely nothing else, okay. So, this is the solution, okay. Now, before we get into solving this, what do you think is the most sort of intuitive coordinate system to solve this problem? Polar coordinates, right. So, I mean in polar coordinates, what will we write your del squared operator? Does anyone remember? Right, no, yeah, no one usually remembers it. So, we will just write it down. So, it is 1 by r this is the operator del squared in polar coordinates. Yeah, you just look up the Wikipedia article or whatever and remember, write it down each time. But I mean, this is still looks complicated. So, what is another simplifying assumption we could do? So, let us try to interpret this equation a little bit physically. I have a left hand side which is some operator and right hand side is an impulse placed at which point? R is equal to r prime, and I want to find out what is the response when I place that impulse at r prime, okay. how can I make my life a little bit easier? I don't want to care about theta. That's the right idea, right? Out of these two derivatives with respect to r and theta, if I can somehow remove the theta dependence, it would make my calculation easier. And what would be the way to do it? If you are standing at the impulse, do you find a angular symmetry about it? Right? If the impulse is at one point and you are standing over there, everything around you looks the same with respect to theta, right? But in our coordinate system right now, this is what we have. Let's say this is our impulses here at r prime, okay, and this is some general point r. So with respect to this observer who is standing at r, right, there is an observer standing over here, the impulse is over here. So is there any angular symmetry for this observer? Not at all. When will there be angular symmetry? If I move r prime to the origin, right? So supposing I do this small transformation over here, I move r prime over here, okay, and this guy r remains over here. Now wherever this observer is with respect to theta, if I keep the same value of r and this observer walks around like this, there is no orientation with respect to theta anymore, right? But has the physics of the problem changed? Not at all. I am just choosing my location of my coordinate system. The origin of my coordinate system is what is being chosen a little bit cleverly. Once I get the solution to this problem, all I have to do is do a shift of origin and I get my general solution. Okay. So we'll, without any loss of generality, so WLOG, without loss of generality, we can start with r prime equal to 0, okay, and consider all points which are away from the origin. Okay. So in this case we have angular symmetry, which means that what is the physical significance of angular symmetry is that whatever function or output I get will not have any theta dependence, right. So no theta dependence, and that's great for me because this guy, the third term in this Laplacian can be set to 0. It is not an approximation, it is exact, right. So let us just put it all together. What do we have then? Our equation becomes del 2 by del r2 g of r. Now I will just write g of r. Why am I writing g of r? I have said r prime equal to 0. So it will get irritating to write it each time. So just g of r, okay, plus 1 by r, okay, and k squared g of r is equal to minus del of r, okay. Again I do not write del of r prime, and here it is understood that this is g of r comma 0. Okay.
So in polar coordinates we have r, theta and phi, right?
This is 2D polar coordinates. You are thinking of 3D cylindrical coordinates or 3D spherical coordinates where there is r, theta and phi, but this is just a 2D problem. So there is no phi. Okay. Yeah, so this is, let us write it over here, 2D polar coordinates. But when we move to the 3D example, we will take spherical polar coordinates again for reasons of symmetry. This is fine, right? So what does this look like? This looks like a second order differential equation, right. There is a 1 by r in the denominator, right. So let's see what we can do with this. Actually I forgot one thing, I am saying r greater than 0. So what should the right hand side actually be? 0, right. So I should not write this over here, I should just write it 0. Okay. We will deal with the singularity, the r is equal to 0 point in the very end, okay, as we had done in the 1D example. Fine. Okay. So now this is the second order homogeneous differential equation that we want to solve. Okay. Let us try to get it into a little bit more of a familiar form. Okay. So to do that, I am going to take this equation and just multiply everywhere by r squared. Okay. I do not like to have the 1 by r in the denominator, so I will just multiply by r square, right. So I am going to get a r squared d2gr by dr2, okay, plus r dg by dr plus k squared r squared g of r is equal to 0. Okay. So, I just multiplied by r squared. Okay. Now, those of you who have done a course on special functions or whatever in your math courses might recall what is called the Bessel's differential equation. This Bessel's differential equation, no one will actually remember, but yeah, I mean, if you look it up, this is what it is. It looks like x squared y double prime plus x y prime plus x squared minus alpha squared y is equal to 0, where alpha is a constant. Okay. So, do you see any similarity between this equation and our equation? It looks almost the same, right? I have a second derivative multiplied by squared, first derivative multiplied by linear term, and x squared y or a r squared g term, right? Something is slightly off, and that is a k, right? So, we will have to deal with that k. We will get to that, but let us just look at the high level conceptual idea here. This being a second order differential equation has two independent solutions, okay, and those solutions are named after Bessel, right. So, these the two solutions are, the two independent solutions are this j alpha x and y alpha x. So, these are called Bessel's functions of the first kind and of the second kind. Okay, so, this guy is the first kind and this guy is the second kind over here. Okay. So, this is just information, I have not derived anything. We got very lucky that our Green's function relation came very similar to a pre-existing differential equation. So, all the hard work was done by the gentleman Bessel for us, we just have to carefully adopt his solution. Okay. So, the Bessel's functions are written in two sort of popular ways. First is this way, which is j and y. The second is linear combinations of j and y. They will also be solutions, right? Linear combinations of j and y will also be solutions. So, that is the second type. So, for example, if I take j plus j times y, I get this guy, that is the definition. So, what is this guy called? It is called a Hankel function. Again, of the first kind and of the second kind. This guy is defined as j minus jy. Okay. So, linear combinations of the original solutions are still solutions to the differential equation, right. So, you can either have Bessel's functions or Hankel's functions which are solutions to this differential equation. How, I am getting a little ahead of myself, but how would you know which solution to take? You have a differential equation, you want to find g, remember that is our objective, because once I find g, I can convolve with f and get my phi. Yeah, so I can write aj plus by, I can also write ah1 plus bh2, both will work. Which one should I choose? When I know it is going to be real, that could be one thing. What is the, in solving electromagnetics problems, what are the two things we have heard of? Maxwell's equations, second thing is boundary conditions. So far we have not talked about boundary conditions. So, boundary conditions are actually what will help us to choose which is the most convenient form. You can choose either representation, but one form may be more convenient than the other. Like we saw the Green's function in 1D, there was a closed form solution or a series solution. Depending on the problem, I will choose one or the other. Okay. So, we will leave that choice for now. So, looking at our differential equation over here, this is not yet exactly in the form of the Bessel's differential equation, because as was pointed out, the factor of k, right. So, first of all, in our problem, what is the value of alpha? Alpha is 0, there is no constant r term, right, alpha equal to 0. So, to convert this equation, how do I convert our equation 1 into equation 2? Put kr as a new variable, right. So, supposing I put kr is equal to x. Okay. So, if I take d psi by dr, that is what I want to worry about, d psi by dr. Psi is any function, I can write it by chain rule as d psi by dx, dx by dr, right, and this becomes what, dx by dr, right. So, that becomes a k, right. So, this becomes k d psi by dx. Okay, this looks weird, dx, yeah. Okay, so with that substitution, what will this equation become? First term. So, r will get substituted as x by k, right. So, I have a x squared by k squared. Second term becomes, will it become k or k squared? K squared, right, because the second derivative, when I apply this chain rule once again, it will become k squared. So, this will become k squared d2 by dx2 g of, let us just write it, let us just write it as r. I can write it as x by k, so same thing. Okay. If you want, I will write it as x by k. Okay. Next term becomes x by k multiplied by k multiplied by d by dx g of x by k, okay, plus x squared g of x by k is equal to 0. So, conveniently for us, all the k's cancel off, and I get exactly the Bessel's differential equation, which is as follows. Okay. So, the general form can be, I know this is exactly the Bessel's differential equation. So, the solution is, I can write down g of x by k is going to be equal to, so let's assume the Hankel form. Okay, I could have assumed in the Bessel form, but I can as well assume the Hankel form. So, a times h 0, because alpha is 0, 1 x plus b times h 0 2 x, right. This is the object inside the differential equation. So, its solution is linear combination of the two solutions. Okay, nothing very great over here. But remember, x is our intermediate variable. I am not really interested in x. So, I should resubstitute and get the solution in terms of r. So, that will become, left hand side becomes g of r is equal to a times x becomes kr, right, and b times h naught 2 of kr. Okay. So, that's how these two functions, that's how the Green's function can be written. So, it seems that without too much effort, because the effort was done by Bessel, we've got some form for the Bessel's for the Green's function. Just one small piece of information: how do these functions j0 and y0, what do they look like? Okay, j0 of r and y0 of r, because that's what h1 and h2 are made of. What do they look like? So, if I plot it over here, let's plot this as x. So, j0 looks something like this. Okay, so this is my j0 of x. Okay, and on the other hand, my y0 actually has a singularity at the origin, and both decay for large r. Okay. So, we should have a physical, a mathematical intuition of what this function looks like, right. So, the mathematical difficulty with this Green's function g is going to happen at which point? R is equal to 0, because that is the point where y is going to blow up. Okay. So this is unlike your Green's function from the 1D example which didn't blow up. This guy is blowing up. So dealing with this is going to be a little bit interesting. Okay.